Students, I'm going to talk to you about Pythagoras today because that's what the lesson's about. I'm not here, obviously, in class, so you can watch this and perhaps get some ideas on what Pythagoras is about. Pythagoras was a Greek dude, lived many years ago, thousands of years ago, and he knew a bit about triangles. And so we're going to be learning about triangles today. So heading down first, let's just put down, and this is lesson 3K, introducing Pythagoras. There it is. Now, like I said, Pythagoras was really good with triangles, but there's one specific type of triangle that Pythagoras worked with. In fact, if you use his equation on these other triangles, other than the one that he used, it won't work. Won't work at all. It only works on right-angled triangles. And you know about right-angled triangles. I'll get you to write it down. Right-angled triangles. And you know what they look like. I'm going to draw one here. There we go, and we indicate that it's a right-angled triangle by using this little square. And again, you've seen that before. I'm sure you've seen that before somewhere. This is a right-angled triangle. They look varied in shape, and we'll have a look at a couple of those in the next couple of minutes. But here is a basic one. There are three sides to it, obviously, and we're interested in those three sides. And Pythagoras was as well. I'm going to call this side A. I'm going to call this side B, and the last side I'm going to call C, despite the fact that that side C has a specific name, and that specific name is the hypotenuse. Yes, you heard right, hypotenuse, and this is how we spell it. Hypotenuse. I hope you can read that. Hypotenuse. You're going to come across it a lot of times in the next few years. But it's the side that is angled. It's angled. It's opposite, and this is the way to pick it every time, it's opposite the right angle. Okay? Opposite the right angle. You can pick that up anytime. You can figure that out anytime. Three sides. Now, Pythagoras came up with an equation that linked each of the three sides. In fact, it's really clever, and I'll get you to write this down too. It goes a squared, so if we take that side there and we square it, if that was 4, then 4 squared would be 16. If we add that side and we add it to the square of the B side, B squared, right? So I've taken this side and squared it, I've taken this side and squared it, and I've added them together, and the number you get, just amazingly, is this side squared, the hypotenuse squared. Hypotenuse squared. And there's lots of patterns in maths, and here is another one. And it's really handy to have because you can find out how long that side is. All right? You're going to be doing some activities next week to find out the length of this side. Actually, using this equation, we can also find out the length of any one of these sides if you know two of them. Got that? All right. Let's do an example of this. Let me show you that it works. All right. Here is a special type of triangle. I'm going to go off here, and I'm going to write or draw this triangle. This triangle I've spun around. Can you see it there? I'm going to put my characteristic right angle in that corner. I'm going to call this side 3 in terms of length. All right? I'm going to call it actually 3 centimetres. Let's do that. 3 centimetres. And then this side here I'm going to call 4 centimetres. And if I drew this on a piece of paper, which I can do, get some graph paper, draw it out, make that one 3 centimetres, make that one 4 centimetres, I could get a ruler, and I could measure this side, and I'd go, Mr. Kunz, why do I need to use the equation? I can measure it. Why do I need to use the equation? Well, the equation is really good because sometimes we end up with triangles that we can't measure. This might be a distance we cannot measure. And again, next week, I'm trying to put together some activities where you won't be able to measure this length because it's either going to be up in the air or it's going to be somewhere where it's difficult to measure. So you could measure this and you would say it is so many centimetres. Well, let's use Pythagoras' theory to work out how long it is. All right? So I'm going to put 3 into where the A is. Now it doesn't matter if 3 goes to B because an A squared plus a B squared is the same as a B squared plus an A squared. You're just adding them together. All right? So I just choose one of the sides and I choose 3 to be A. All right? So I'll write my equation across here. Can you still see it? I'm going to go A squared, did it wrong, plus B squared equals C squared. I put a 3 in here, that's where my 3 is going, and in here, you guessed it, that's where my 4 is going. All right. 4 in here. So what's 3 squared? You know what the answer is. 3 squared is 9. 4 squared, what's 4 squared? 16. Easy. 16. Put the plus in the middle. 9 and 16 equals 25. Very good. So that equals 25. Now 25 is what C squared equals. All right? 25 is C squared. Do we want to know C squared? Not a chance. We don't want to know C squared. We want to know what C is. C is a number that was multiplied by itself to give 25. C is a number that is multiplied by itself to give 25. And you've guessed what the answer is. You've guessed that C equals 5. And you'd be absolutely right. Well, how do we do that mathematically? How do we do that mathematically? If I was to say C squared equals 25, then to find C, I would write C equals the square root of 25. All right? That's how we do it mathematically. C is the square root of 25. Now, to find the answer, you can plug it in your calculator if you're not really good at maths, but you'll know that the square root of 25 is 5. So the length of this side, which is the hypotenuse, is 5 centimetres. Got it? I'll write it in there. 5 centimetres. Pretty cool, eh? Pretty cool. Now, this only works with right-angled triangles. Let me rub out this bit over here. It only works with right-angled triangles. And you would find that it doesn't work with any other triangle. Let's try that out. And it's a really good way of finding out whether a triangle is right-angled or not. If it only works with right-angled triangles, then you can find that out. Let's do an example of that. Here we go. Here is a triangle. A standard-looking triangle. Right angle in this corner. This side is called the hypotenuse. Let's give it a number. A good number is 6. We'll give it the number 6. This side here, what number do you want? All right, let's make that 2. And this side here, we'll make that, that looks probably about 5. Is it a right angle triangle? Am I tricking you? Is it a right angle triangle? And you're probably going to pick up that no, it's not. But let's prove it. Is it a right angle triangle? Well, if it is, then Pythagoras, his theorem, is going to work. If it's true, it's right angled. If it doesn't work, it's not right angled. Let's write it down. A squared plus B squared equals C squared. Got it? All right. A, I'm going to pick 2. It can be either the 2 or the 5, but it's certainly not the 6 because the 6 goes here. All right. So 2 squared plus 5 squared equals, well, the 6 is there as the hypotenuse, 6 squared. Now, is it true? Let's find out. 2 squared is 4. 5 squared is 25. 6 squared is 36. Is that true? I think it doesn't take very long to figure out that it's not true. Okay, so I'm going to put a line through here. This adds to 29 is not equal to 36. And because we've done that, because we know that 29 is not equal to 36, this cannot be a right-angled triangle. So it's a good test of right-angled triangles. Now, what else do we need to know for this lesson? Let me look at the textbook. That's about it.